All right, this is section 5.1, ratios and rates. And this first example here says match each description with a verbal rate. Match each verbal rate with a numerical rate, and then give a reasonable numerical rate for each description. So the description for the first one says your running rate in a 100-meter dash. So there's that word rate that we'll talk about. And this means your speed. And if you're looking at the verbal rate, there's really only one speed that kind of makes, or only one verbal rate that makes sense here, and that would be meters per second. So I would say that the running rate would match with that. And then in terms of the numerical rate, what does it actually look like when you write it? I see M for meters, and I see seconds down here, and that would be right there. And maybe a reasonable rate, meters per second, maybe someone's running 8 meters per second. That's just kind of an estimate. Obviously, a meter's a little bit close to a yard. But at full speed, you might be able to get 8 of those in a second. The second one says the fertilization rate for an apple orchard. So if I was applying fertilizer to an apple orchard, it wouldn't be dollars per year, although the fertilizer does cost money. It wouldn't be inches by year because that's not how fertilizer is measured. It'd be pounds. I'd buy fertilizer in bags, obviously for pounds here. And pounds per acre would be this one up here. And maybe I'm applying, 10, 20 pounds per acre maybe. It depends on how big your apple or how many trees you have per acre. The next one says the average pay rate of a professional athlete, and that's going to be in dollars per year, and that would be this one down here. And depending on what sport you play and which athlete you are, this could be really high, but it does say average pay rate. Most professional athletes aren't, obviously some are really, really good, but most are not. So maybe an average pay rate would be $600,000 a year, depending on what sport you're playing. And then the next one says the average rainfall rate. So the only one we have left is inches. So inches per year, which is up here. And again, depending on where you are, if you're in Kokomo, maybe we get 20 to 25 inches a year, something like that. Just really depends on where you're at. So these numerical rates are how you would write these rates out in a problem. And maybe you've seen that before. Like, for example, miles per hour is a speed, but it would be a rate. Teachers per student would be another one. So these are all just examples of what rates are. All right, so here's our vocab for this section. A ratio is a comparison of two quantities using division. So you can make it look like a fraction, or you can use words, or you can use a colon. That's called a colon right there. All of them say 3 to 4. So I know it looks like 3/4, and a lot of times you can treat ratios as a fraction, but we would say if it's ratio, we'd say 3 to 4. So 3 students for every 4 groups or something like that. And then the next one, a rate is a ratio of two quantities with different labels. So what makes a rate different from a ratio is that now we have labels. So instead of just saying 60 to 2, we have 60 miles for every 2 hours. And that's called a rate. So now we know what we're talking about. Not just two regular numbers, but we have a distance in miles, we have a time in hours, and that gives us a speed. This particular rate would be a speed, 60 miles in 2 hours. But most people wouldn't say 60 miles in 2 hours. When people give their speed, they say miles per hour, and that hour is singular. So a unit rate is a rate with a denominator of 1, and we call it a unit rate because the bottom number is 1 unit. So instead of saying 60 miles in 2 hours, I could say I'm going 30 miles per hour, which is actually the exact same. These are the same rates. One has just been simplified. 60 over 2 is the same as 30, or 30 over 1. So 60 miles in 2 hours is the same as 30 miles per hour. And we love to use unit rates because they're already reduced. And I just realized I spelled labels wrong. That should be LABELS. So kudos to anyone who caught me on that. Maybe you didn't catch me. All right, so why are unit rates so helpful? Well, if you look at this next one, it says snorkel rentals are $8.75 per hour at this one company, the orange company, and at the red company, snorkel rentals are $7.25 per hour. So both of them are unit rates because they say per hour, and that hour is singular. It's just one. So I guess if you wrote it, you'd say $8.75, so $8.75 per hour, or 1 hour. So it's a unit rate for both of them. But why are they so helpful? Because it makes it really easy to compare the two values. So obviously I know the red company would be cheaper because they offer a lower unit rate per hour for their snorkel rentals. So how do I find a unit rate? Well, these two are already unit rates, but if I just have a regular, just a rate like the last one, 60 over 2, it's pretty simple. All we have to do is divide the numbers and the labels. Kind of interesting. You think, how do you divide a label? Well, if it says dollars per hour, we put dollars divided by or slash hours. So we can do a couple examples. Let's go back to ratios, though. This first example says there are 45 males and 60 females in a subway car. The subway car travels 2.5 miles in 5 minutes. Find the ratio of males to females. All right, so males, we know there's 45. And females, we know there's 60. So we can write it as a fraction. You can write a ratio as a fraction, 45 to 60. And then just like all other fractions, we would want to reduce this. So that's why we were reducing so much on our Chapter 5 opener. So there's a number that goes into both of these, and it's 5, but there's a bigger one. You can actually take 15 out. So if you divide top and bottom by 15, think like a clock here, then 15 goes into 45 3 times, 15 goes into 60 4 times. So our ratio actually reduces to 3/4, which means there are 3 males for every 4 females. So obviously there's more females. All right, part B says find the ratio of females to total passengers. Okay, so not females to boys. We're not just flipping around, although that's what you would do if it said females to males. But it says females, which again was 60, to total passengers. So if you take 45 males and add it with 60 females, that's going to give us the total of 105. So there are 105. And again, both of these numbers are divisible by 15. So we can reduce this ratio. We just said 15 goes into 60 4 times. So I think 60, 75 would be 5 times. 90 would be 6 times, and 105 would be 7 times. So there are 4 females to every 7 passengers. Now, that's one way you can get your answer. Another way that might have been even a little bit easier is to use the ratio we already had up here and say, well, if there's 3 boys to every 4 girls, then I can add those, and that's how we can get our 7 for our denominator here without having to reduce. Right? We can say, well, that reduces to 4 girls for every 7 total passengers, and that also gives us 4/7. And then the part C here says find the speed or the unit rate of the subway car. And remember, to find a unit rate, you just divide. It's really, really simple, and you can use your calculator, so it's not going to take you very long. So the unit rate, when we do speed, we usually do distance over time. So we want to do the miles divided by the minutes. This isn't hours this time. We're talking about a subway car, so it's not going to be going hours, just minutes to get it to our destination. So 2.5, and that's miles. So I put MI divided by 5 minutes. So MINS for minutes. And then we can use our calculator to divide that. And 2.5 divided by 5 is going to give you a half, or 0.5. But we have to label it. Not only do we want to divide the numbers, but we also want to divide the labels. So we put miles / minutes. And the way that I read this or I guess I don't have to put the last S now because it's singular. The way I read this is half a mile per minute. And that tells me how fast the car is going at a much easier rate for me to understand. Okay, I know the car is moving a half mile every minute. So if I know I'm supposed to go a full mile, that would take me 2 minutes, and so on and so forth. So using the unit rate is a much easier way to do this. So all you have to do is divide, and you divide the number, and then you put the labels. You need to put 2 labels. It's really important that you put both. All right, so let's review for just a second. All ratios, we said, must be reduced, and all rates must be labeled. That's really important. Labels are going to be super, super important. All right, this next problem says the ratio table shows the costs for 4 different amounts of artificial turf. Find the unit rate in dollars per square foot. Now, if you know, obviously there's a lot of schools that have been putting artificial turf in for their football fields and baseball fields, and it's really expensive. And this chart shows, I don't know what kind of turf this is, but it shows the amount that you're getting in square feet and the cost. So 25 square feet would cost you $100. Now 25 square feet, just to give you an idea, would be a 5 foot by 5 foot square. So maybe you're 5 feet tall. So imagine your height if you're laying down on the ground, and then someone stacked you again, try to make a square out of you. That's not a whole lot of space if you're talking about, say, a football field. And that right there cost $100. So it's really expensive for turf. So if you buy 100 square feet, you get $400. You can see how all these rates are being times by 4. They're all equivalent rates. So they're all equal. So I would like to find the unit rates. And then it says right here, it gives you the key in dollars per square foot. That means they want you to take the dollar amount first, which is actually on bottom, and put the square feet and divide by that. So $100 divided by 25 square feet, which remember you can write square feet like this. And so I'm going to divide those two numbers, 100 divided by 25. Remember, that's how I find a unit rate. So I'm finding a unit rate here. So 100 divided by 25 is 4. And then I'm going to do my label. So dollars actually goes, the dollar sign actually goes in front, per square foot. $4 for a tiny square foot. And that's why it's so expensive to turf in those fields. And we can use this rate, we could use this one here, because they're all equivalent. So you could do $400 divided by 100 square feet, and that's still going to give you 4, because 100 goes into 400 4 times. All of them are going to give you the same one of $4 per square feet. So you can actually use any of those rates from that table. Here's another one with another table. It says, this table shows the amount of money you can raise by working concessions at a school basketball game. So if you work 6 hours, you will make $90. If you work 12 hours, you can make $180. So you can see what they did is they just multiplied that first ratio by 2. Okay, and then you could say they multiplied by 3 to get this one, and then they multiplied by 4 to get that one. So these are all equivalent ratios. All I have to do to find the unit rate is I can take one of them, say the first one, okay, and it says the amount of money you could make working sessions. I would obviously be doing dollars per hour here, so I'm going to put $90 divided by 6 hours. We can abbreviate everything there. So I take my calculator, I do 90 divided by 6, and that gives me 15, and then I'm going to put dollars per hour. So that's how much money we make working in the concession stand. And it doesn't matter if you use the first rate, if you use the second one, 180 divided by 12, you can check it, is still 15. You just have to make sure you're doing it in the right order. When you work a job, you're going to get so much money per hour, dollars per hour. We don't say hours per dollar. Like, I wouldn't want to take the number of hours and divide it by dollars. That wouldn't make sense. I would take dollars first and divide it by hours to figure out what my hourly rate is. All right, so sometimes when you're doing these unit rates, you end up getting fractions inside of your fraction, if that makes sense. And we call those complex fractions. A complex fraction has at least one fraction in the numerator or the denominator or both. So these are examples down here of complex fractions. The first one says half a cup per 4 fluid ounces. So maybe you're making a recipe that requires half a cup of sugar for every 4 fluid ounces of milk or water. So to find the unit rate, which is again, that's what we're trying to do here, we're just going to divide. So how do you do that if there's a fraction in there? Well, you just use your fraction rules, right? 1/2 divided by 4, or 4/1, is the same as 1/2 times 1/4, which is 1/8, and now I can label cup per fluid ounce. OZ is actually the abbreviation for ounce. If you're a recipe person, you probably know that if you do some cooking. Letter B says 2 inches for every 3/4 of a second. So this would be a speed, maybe not a very fast speed. Maybe that's talking about 2 inches isn't very far to move, but it's not a very fast one. But we can do top 2/1 divided by 3/4. So we're still dividing like we do with unit rates, but we're just using our fraction rules. 2/1 times 4/3. Nothing cancels there. So 8/3, and that would be inches per, so I can put my slash, just like they had a slash right there, per second. And then the last one, they are both fractions. So top 3/8 cup of sugar divided by 3/5 cup of flour. So another recipe. So 3/8 times 5/3. Keep, change, flip. The 3's cancel, and you get 5/8. And then we label. It's really important we label. So 5/8 cups of sugar per cup of flour. So 5/8 cup of sugar for every 1 cup of flour. Maybe that makes more sense, right? Because we can keep track of just a single cup of flour better, just like we can keep track of a single second or a single fluid ounce. All of the denominators are 1. Why am I not writing the 1? Because it's implied that it's singular. You don't need to write it. Just like when I write x equals 4, I don't write 1x. It's just implied that it's there. So all these denominators are 1, which makes them unit rates. All right, the graph shows the speed of a subway car. Find the speed in miles per minute, right? There's the key. They're telling us how they want us to divide miles per minute. Compare the speed to the speed of the first subway car that we did in the first example. Now, remember, all the way from the first example, I won't make you rewind, but the first example, the subway car was traveling 0.5, remember, half a mile per minute. So that's how fast the first subway car was going. So to do this, it's kind of interesting. They give us this nice little chart that says distance, and then it's on the y-axis here, and it says time in minutes on the x-axis, and it gives us this chart, and you can see as time is going farther, or time's going on, the distance is increasing. You can see the line going uphill here. So we can pick any point to find our speed of the subway car, any point that's on the line, and they give us 2 of them. 2 useful ones, I should say. They actually give us this 0, 0, which means at 0 minutes the subway car has not moved, which makes sense, but you can't do 0 divided by 0 to find your speed. You got to wait for it to move first. So we'll use that one. But I want to do distance divided by time. That's how you find speed, anytime, not just in math, but when you do this in science too. You do distance divided by time. Our distance is on the y-axis. Well, the y-coordinate is the 1 and 1/2. And you can see, if you go over, if you draw a line, that's right there at 1 and 1/2. So our distance is 1 and 1/2 miles. And our time is the x-coordinate, because it's on the x-axis. This is the x-axis. And it's 3. And you can see the point, if you draw a line down from that point, right there at 3 on the x-axis. So 1 and 1/2 divided by 3 minutes. All right, so we divide 1 and 1/2 divided by 3, which is the same as, actually, you know what would be easier? Just use your calculator and write this as a decimal. 1 and 1/2 is just 1.5. That would be really easy. Just do 1.5 miles divided by 3. And 1.5 divided by 3 is 0.5 and miles per minute. And what we can figure out is actually it's the same speed as the first subway car. Maybe not the exact same car, but it must be the same company or whatever that's using the same speed. So it's moving half a mile per minute. All right, so what I want to look at now is what would have happened if we would have used this other point, this first point here, this 1/2, 1/4. So let's try that. Our distance, remember, was the y coordinate, the y, and that is the y coordinate is the 1/4, so 1/4 miles divided by, and our time was on the x-axis here, and that was in minutes, and the x-coordinate, so that's the y. The x-coordinate is this one here, so divided by 1/2 minute. Okay, so then I can do top divided by bottom. I can keep change flip, and I can cancel, and that becomes 1/2. So I get 1/2 mile per minute. But you know what? That's the exact same as 0.5. So you get the exact same answer. In fact, you could even, instead of using fractions, if you wanted to not use fractions, you could call this 0.25. Again, that's the nice thing about knowing these fractions, knowing these simple ones. What are they as decimals? 0.25 divided by 0.5 would give you 0.5. And so we get the same answer. And why do we get the same answer? Because this is a line. So no matter what point I use on this line, it's going to be the same because it's constant. It's a constant rate of change here. The subway car, no matter where you're at, is going the same speed. So why is it increasing? Because it's not tracking the speed, it's tracking the distance. So what's increasing is the distance. The speed's actually staying the same. If it was changing speeds, it would look like this. It would go up and it'd go down and go up and go down, and that would show you that the speed is changing. But it's a constant speed here. And you know what? I'll even do you one better. I see even a better point we probably could have used that's also on this line. What about this one right here? Why can't we use that point right there? They didn't mark it as 1, but you know what? We could still use it. It looks like the y coordinate is 3 and the x coordinate is 6. So 3 miles for every 6 minutes. But you know what? That's just going to reduce to 1/2. Or if you do top divided by bottom, you're going to get 0.5 again, miles per minute. And that is the same exact thing. So you can actually use any point on this line except for this 0, 0 that we talked about, because you can't do 0 divided by 0. You'll get an undefined answer. So an interesting problem there with the graph. All right, so this is the last one we'll do for this lesson then. It says it's another graph. The graph shows the distance that you walk. Find your rate in feet per second. And that is a unit rate, and I know it's a unit rate because it said second. So per second, that's 1 second. So it is a unit rate. And feet is measured on the y-axis again, and seconds is measured on the x-axis. So my y-coordinate, I can use any of these points because they're on the line. I can use 11. Right there's my y, so 11 feet. I'm walking 11 feet, and it takes me 2 seconds to do that. So 11 feet for every 2 seconds, and then to find a unit rate, I just divide. That's really all we're doing in this whole section is just dividing. So 11 divided by 2, use your calculator, gives you 5.5, 5.5 feet per second. Try the other one, 22 divided by 4. If you do 22 divided by 4, yep, it gives you 5.5. It's a constant rate. You're walking the same speed. So that's how you find unit rates. And that's the end of section 5.1.